So there has to be something more, and we are looking at, like, regularly or all the time in different corners of standard model, but it seems to be hiding really well from us so
I
far.
see.
This small magnet compared to the entire Earth's gravity,
Yeah.
and it can still win over it
Yes.
to lift the screw.
That
Well,
is really
that's-
fascinating. Yes.
That's how strong.
yeah,
That's
yeah.
how weak gravity is. In 1890s, when people were walking on streets saying that somebody discovered the electron, what is the use of it? Nobody
yes,
knew.
yes.
Today, 130 years later, you can't do anything without the electron. Like,
Exactly.
all of internet, all of electricity, everything works on the electron. The job of a physicist or fundamental science is to answer questions. Doesn't matter if the question is relevant for today or not. Some journalist actually asked a physicist if it's possible that we can create a black hole at the Large Hadron Collider. And being a physicist, he was very conservative in his answers because the probability of any process is non-zero. He said, yes, it's possible. The simplest association, at least for
Yes,
people
yes.
in Europe, is that it's their money. The amount of data that we have is basically, you won't find it anywhere in industry that this large. Even Google has less data than what we
Then,
have.
sir. Max Planck, one of the greatest minds in the area of particle physics, once said that we humans are not meant to solve the mystery of the whole universe, because ultimately we are the last puzzle key of solving the universe. But here we are, trying to defy the words of Max Planck, and still we are searching the origin of the universe. So today we have a very special guest for our podcast, Mr. Naman Kumar Bhalla. He's a particle physicist who works closely in the area of particle detection and all these things. So welcome, Naman.
Thank you.
Yeah.
Very happy to be here.
Good to see you. And we will, as usual, we will start with a small introduction for our audience, that who you are. It would be great if you can introduce yourself.
Sure. So I'm Naman. I was born and raised in Delhi, and I started with my bachelor's also there in Delhi Technological University, doing engineering physics, where I was majoring in electronics, but I had a minors in nuclear engineering. And I think with this studies of nuclear engineering and all the physics courses that we had there, I got interested into fundamental physics. So I started with a course in Masters of Physics in Göttingen in Germany. And yeah, there I got into particle physics, and now I'm in Freiburg doing my Ph.D. in a similar field.
Great. So, from where should I start? How are you feeling? First of all, let's start with this. And how are you feeling today?
Very happy. It's very warm outside, so after biking a while, I'm very active.
Feeling
and also
excited.
very happy.
Okay.
Yeah, very excited for the podcast as well. So
I mean, nowadays the weather is pretty good, I would say.
Yeah.
It's similar to what we have, the Vasant season.
Exactly.
It's quite similar to it. Not too cold, not too hot. Yeah. Okay. So I would like to start with the basic question. What do you think about when somebody asks you about what is a particle?
Okay, so my way of approaching this is just trying to figure out what everything is made up of. You can have let's say, for example, Legos. So you build a house with Legos, but each Lego is basically a brick that you use to build that house. But that Lego is not a particle itself. It's a component, but you can still break it down into, for example, molecules, and those molecules are then further made up of atoms. Those atoms have protons and electrons. The electron is, so far as we know, is fundamental, but then the proton itself, or also the neutron, can then further be broken down into quarks. And these, so far that we understand, we haven't got down deeper. Maybe there is even something more fundamental, but so far these are the fundamental particles.
Fundamental particles.
This is what we call the particles that make up everything that we see around us in the universe.
But then now my question is actually, what are the criterias that define that, okay, this particle is a fundamental particle? Like, for example, you said that electron is considered, or proton is considered, or neutron is considered as a fundamental particle. Then what are the criterias of describing or saying that, okay, this particle is a fundamental particle?
The criteria so far has always been how deep we can look, to be honest. It's the energy regime that we have reached, because the higher you go on energies, the lower you can get in size. And because we cannot define a radius or a size of the electron or these fundamental particles, because we can't see it or how big they are, to us they seem point-like. And because it's just point-like, it's in principle zero dimensional. For us, we call it fundamental.
Fundamental.
Exactly.
So basically what you're saying is that when you are not able to break it
Yes.
further,
Yes.
then you will say that it's a fundamental particle.
Exactly.
I see.
When
I
we
see.
can't, when our resolution cannot resolve them anymore, the size of the particle is when we call them a
Okay,
fundamental particle.
but then there is also a kind of a confusion, especially for people who are studying science for the first time. What is wave particle duality?
Yes.
There is a particle, and then we also associate any particle with a wave. We also say that even you as a human, you can be also considered as a wave,
Yes.
but it's provided that you have a very large wavelength.
Yes, this is actually a bit not so easy to answer. So the thing is, we say that everything has two forms. It's either a particle and wave, and actually both simultaneously. The thing is, let's say for an electron will have its impact as a wave that goes beyond into space on some certain radius or maybe something further. But when you try to observe that particle, when you try to really put down or precisely measure its position, then it's point-like, and it suddenly basically collapses into one state.
I see.
So
it's a concept of wave function
exactly.
collapsing.
It's the Heisenberg uncertainty principle.
Heisenberg uncertainty principle. Yeah.
Yes. So you can feel its impact to a certain distance, but because when you start observing it, it collapses, and that also makes a bit of sense in the sense, like, if you try to think about how we observe something with our eyes, it's like a particle of light. So, for example, a photon will basically go and hit something. It will reflect from it, and then it will come to your eyes, and you will see it. Right. It's also how it works. For example, with fundamental particles, that some particle, like for example a photon, maybe another electron, will hit the other electron and then come back, and we will see it. But because it's hitting it, and now both the particles have similar mass or energy, it changes its position just by hitting it.
It's mostly like a billiard balls.
Exactly.
If the steady ball is there, and you throw another ball which has some momentum and energy, the energy and momentum will be transferred.
Yes.
It's very similar to that.
Exactly.
Right?
So you will see it that it was there, but now it's not there anymore because you moved it. With your observation.
Okay. So interestingly, since we have already are talking about fundamental particles, and I will go a little bit step forward towards asking you questions about the fundamental model of particles. The quarks, gluons, muons, and nowadays there is a very interesting particle that has originated, the Higgs boson.
Yes.
We will talk about it in detail, but we will start with this thing. What is this fundamental or the basic model that we use, and why it has sustained for so long? That why because I heard a lot of stories that every second year there is a new theory of a new model of particle which originates in particle physics.
Yes. Yeah. It's again very, very interesting question. The thing is, so we call this the standard model of particle physics right now, which has the current particle content. So all the matter particles, so the quarks and the leptons, and then the bosons for gauge interactions or force carriers, for example.
We will sorry to interrupt you, but I think our audience is not very much in depth of these things.
Yes,
so I would really ask you to please partition all these things in a simple or in a more fundamental way.
Okay. So there are the matter particles that make up the matter, and then there are particles that help them interact between them.
I see.
So these interaction particles are what we call bosons, the gauge bosons.
Okay.
And then there is the Higgs boson, which is responsible for giving mass to all the fundamental particles, so including the bosons and the matter particles, which we call fermions. The reason why there are so many theories that keep coming up is because there are so many open questions in the standard model. It is not able to answer a lot of questions, and we know that it is incomplete. So there has to be something more, and we are looking at, like, regularly or all the time in different corners of standard model, but it seems to be hiding really well from us so far.
I see. Okay.
Yeah, we've gone to extreme precisions by now in some cases, and it still seems to be very valid.
Then you talked about that we have already reached to an extreme level of precision. So now my next question is, what is next? Like, when you say that it's an extreme level of precision, what exactly are you measuring? My question is like this.
So there are a lot of processes. So you can measure, for example, the mass of particles, which are indirectly related to some very important parameters of the model. or you can measure, let's say, the probability of a process happening. And that, of course, like the probability is defined in mathematical calculations from these parameters. So the idea is to constrain the parameters of the free parameters of standard model that and try to see how far it still agrees with the theory.
I see.
If we see some deviations in our measurements, then we know that this is the direction to go to find something new in physics. But so far, we haven't been able to find some very significant deviation from the model.
Okay, so in the standard model, the one particle which actually fascinated me a lot, and it sounds a little bit childish, but the reason why I got fascinated is because of a Marvel superhero character, and his name was Graviton.
Okay.
Yes. So I was actually watching those cartoon, and then the guy was able to control gravity. And then I looked into the standard model. I was like, okay, there is one particle which is associated with gravity. So what is this gravity and graviton, and why is it still in the standard model? We have never heard about graviton that any type of experiments have found out this particle graviton.
Honestly, graviton is not part of the standard model. The standard model does not cover gravity at all, and this is one of the biggest open questions we have, because of course gravity is the force we see everywhere all the time. But we haven't been able to find its quantum understanding in that sense.
I see. So it's mostly like a
hypothesized particle that people keep looking for in experiments. There are a lot of searches for it, but so far again we haven't found it. The thing is, we expect gravity to play a role because gravity is so weak compared to other forces. We expect it to start playing a role at very high energies, energies that are, I don't know, some generations away from us at least.
So I think what is the maximum energy limit that we have reached till now in our experiments?
So currently the highest energy is at the Large Hadron Collider at S1, which is currently running at 13.6 tera electron volts, which is, let's say, 13,000 giga electron volts.
Okay. So for our audience, can you please tell that what is the simple example that how large is this energy? Can you give a simple example for that?
It basically means you take a proton. So it's not, to be honest, it's not a very large energy for your regular life, but it's large in the sense that you're giving all of this energy to just one particle. Exactly. And then it's very large because it's just a beam of protons. Every proton is traveling almost at the speed of light. It's like 99.998% of the speed of light, and that is of course a massive amount of energy. If you get something, even a dust particle, to the speed of light and throw it at Earth, the Earth will collapse.
Yes. I actually was reading an article about what if you throw a needle at specific speed near the speed of light towards Earth, and it will nearly damage the whole Earth.
Exactly.
The collapse of that needle would be 10 to 20 or 30,000 times more than what the asteroid did to the Earth when we had dinosaurs on Earth. It was really interesting, and I think that's what we are creating in CERN, right?
So that is the idea.
In a controlled way, obviously.
Exactly, in a much more controlled way. Also, that is also the reason why we have this difference of 0.02% from the speed of light. That's what saves us from the speed, actually. So that difference is a lot because as you converge towards the speed of light, it gets harder and harder to achieve it because you need more and more energy to really get to that speed.
Get to that speed.
So yes, in that sense, sorry, I forgot what the original question for this was.
I was asking about this particle graviton and why it's not yet discovered.
So this is the energy that we have with the protons of 13.6 tera electron volts. The graviton, so as you mentioned, should be visible to us, or what is expected is at 10 raised to the power 11 giga electron volts. So we are 13,000 we are 13,000 giga electron volts. This is 10 raised to the power 11.
I see.
So we are
a tremendous amount of energy.
Exactly.
Not in terms of like real life, but the gap is very big.
It's 7 orders of magnitude away. So graviton is really far, and people, whenever I tell people about the fact that gravity is very weak, they ask us like, gravity is everywhere you see it. It's one of the most dominant forces you see around yourself. But it's an interesting thing to think that, let's say if I have a needle in my hand, right? Or let's say there's a needle lying around or a screw and I want to pick it up with a small magnet. It's very easy. I can just put it above it. It'll pick it up. But this small magnet compared to the entire Earth's gravity, and it can still win over it to lift the screw.
That is really fascinating. Yes,
that's how strong. That's how weak gravity is, really.
But still, it controls. Okay, we are going a little bit off the topic. But as far as I know, as far as I have read and learned about general theory of relativity, gravity is a concept which originates from space-time continuum.
Yes.
Like in simple words, if I say that what is gravity? Gravity is nothing but a dip in the space-time continuum.
Sure.
Right. So if you, it's like if you have a muslin cloth and occupied by four, tied by four different sides,
Yes.
and you put a heavy ball over it, there will be a dip.
Yes.
So in simple words, this muslin cloth is a space-time gravity, and the weight, that the mass that we're talking about, is creating gravity.
Yes,
right.
That's right. The only issue with this is that it's the classical understanding of gravity. We don't have a quantum understanding is our problem.
And what is it, like the quantum
so the quantum understanding is how to fit in, let's say, a model of gravity into a standard model, for which we need some framework, some theory within the framework of quantum field theories.
Yes.
Which means you need a quantum particle for gravity, which, as we said, we hypothesize is that it has graviton. And then how it interacts with matter, and then we want to experimentally find it. So there are some theories that theories of gravity on the quantum level, but they have their problems itself, because it's the math actually breaks down when you go to higher energy. So
yes, I think that's the similar thing that I'm a condensed matter physicist, so we also encounter the similar kind of problem for van der Waals forces.
Yes.
So in a very crude way, it is possible to explain
Yes.
van der Waals forces by dispersion London and one more different type of force. But when you want to make people understand based on quantum level, it more or less breakdowns. It does not give a very clear explanation that from where this van der Waals force is coming.
Yes, so we have a classical understanding of gravity, but we don't have a quantum understanding of it. That's the problem we have.
Yes. So in your last statement, I'm not able to understand two basic things. One is what makes the particle to be compatible to be fitted in the standard model. What's the criteria that this particle satisfies this particular condition, and now it has to be put inside the standard model. It is possible to fit that particle into the standard model. Like for example, the Higgs boson. Yes. So that's my question. Like what is making that particle to fit in the standard model?
The Higgs boson actually was the other case. We needed the Higgs boson to actually make the model complete.
Now my question is, what are the criteria that make the model complete?
So there are a lot of these mathematical things that we call symmetries that are that the standard model has, something like parity. So example, if you look at it, if you change the space coordinates, the physics should not change. So
I'm highly sure that our audience is not really very much aware about the parity, the concept of parity, and reversing of the what do you say? Time reversal symmetry.
Yes. So there, I will then just say overall that there are a lot of symmetries that these particles should follow. So it's not just the particle itself. It actually means how it interacts with all the other particles. And these interactions have their own symmetries that needs to be followed.
Okay. So in simple words, what we are trying to say that there are specific constraints to satisfy for a particle to be associated or to be fitted in the standard model. So there are two basic things. One has Naman has already mentioned about the parity, and the second one I think is the time reversal symmetry. It should follow the concept of. So there are one or two more.
There are
a few more that should be satisfied for the particle to be fitted in the standard model. Okay, that's much clear to me now. Okay, so now that my second question is, it's a very crude one, obviously. Why is it important? Why the hell we are interested in exploring these particles and all these things? Why?
It's a question of time, to be honest. Like there are all these fundamental research. What we get out of this is never understood at the same moment. For example, in 1890s, when people were walking on streets saying that somebody discovered the electron, what is the use of it?
Yes.
Today, 130 years later, you can't do anything without the electron. Like
exactly.
All of internet, all of electricity, everything works on the electron. Similarly for quantum mechanics, they were doing it 100 years ago. Today we're building quantum computers. Who knew back then? It's a question of you. So from my point of view, the job of a physicist or fundamental science is to answer questions. Doesn't matter if the question is relevant for today or not. And then later in time, when it's the job of for example, engineers to use that knowledge to find solutions to problems
to the real world
are
problems.
actually relevant there.
Yes.
If you don't have the
Wisely said,
knowledge
yeah.
in the first place, you can't find solutions.
True. I totally agree on that.
So
That's true.
there is this saying in Hindi, but for the audience, I'll just translate it to English.
Sure.
It says that you can't start building a well when you're thirsty. The well has to be there before.
Wisely said.
Yeah,
that is true. So basically, what we are doing here as physicists or people or the physicists who are working in fundamental sciences, we are just trying to create a well already for the people to drink water when they actually need it.
When they're actually thirsty in the
Yes.
future, exactly.
That is so true. Okay, so now I will shift a little bit towards the more science fiction part. And the science fiction part is there were a lot of hypothetical scenarios that were created when the Large Hadron Collider, the CERN, was at the verge of starting. You know, the people were saying that this could create a black hole, or what benefit is it going to do for the human life and all these things. So I would really appreciate if you can elaborate, or if you can break down these problems, or the myths that were created during that time, and why they were created.
So the reason why, so for example, if I come to the first one, you said the creation of black hole.
Yeah.
The reason why it was created is because this is actually true. Some journalist actually asked a physicist if it's possible that we can create a black hole at the Large Hadron Collider. And being a physicist, he was very conservative in his answers because the probability of any process is non-zero. He said, yes, it's possible. That was actually true. That's what happened. But the thing is, the probability is so low, it's nearly zero. And also the black holes, I mean, to be honest, we do create black holes at Large Hadron Collider, but they are so short-lived and so small that they just decay in less than, I don't know, very short times. I don't know, it's like picoseconds. So it's very small times.
Is it possible by any chance that if we tweak in some parameters or do some changes, can we create really black holes in sun? Like large ones, which can actually destroy Earth?
I think
or consume Earth?
There is a mass limit. I might be wrong, but this is what I remember. There is a mass limit, or a minimum mass limit you need to actually create a stable black hole. And the amount of protons that we have in the ring that are going around do not satisfy that mass limit. So it will never happen.
Okay.
It will never be stable.
It will never be stable. In simple words, we are saying that we do not have enough mass to create a stable black hole.
Exactly. Because there are a lot of protons going around in the ring, but it's still just very small protons. It's not enough mass.
Yeah. But then now I understand that why the black holes are only created when two neutron stars or some different type of stars are collapsing. Very heavy stars.
Exactly.
It's largely related to the relation between mass and gravity.
Exactly.
Right. Yeah. Okay.
I mean, there was someone was trying to calculate what the size of a black hole would be, which has mass of the Earth, which will it won't be stable, so it won't happen.
It won't happen.
Yeah, so that if Earth turned into a black hole, it will be the size of a marble. That's how condensed the mass is.
Okay, so the crux of the whole conversation is that we are safe.
Yes, we are safe. There is a huge safety team.
Okay. This is a good relief.
Exactly.
Okay, so this is one myth that we have busted today, that yes, we do create black holes at CERN, but they are short-lived and we do not have to worry about them. So all the thing that the Earth will be destroyed and all these things, it's more or less a gibberish, I think.
Yes.
Okay, now coming to the second question. I'm sure that exploring the existence of Higgs Boson was not the only experiment that we did at CERN. Till today, we are doing multiple experiments. So can you please elaborate? Because I think the general audience do not really go beyond the understanding of Higgs boson. And the reason is because it was publicized extensively.
Yes. So there are really a lot of research going on at CERN, at the Large Hadron Collider, which is one part, maybe the biggest project, but one part of CERN. So there are I don't know, if I try to really quantify it, it's about 100 papers coming out every year from one collaboration itself.
From one collaboration.
So that's a lot of research. So the idea is they are trying to really look into every process, so every kind of interaction that is possible in the standard model between any 2 or 3 particles, and try to measure the probability of that happening. What is the strength of that interaction? And then because there are so many particles, you have from permutation and combination, so many possibilities of processes. You measure all of them, even the very rare ones, and that's how you get to so many so much research, or such a huge research.
I see. So it's more like we are trying to explore every single possibility, not every, but most probable possibilities by going through all this. Colliding the particles.
Yeah.
Okay.
Exactly.
So,
as much as we are sensitive, we can be sensitive.
As much as we can be sensitive.
Exactly.
Okay. Now my question is, what exactly do we measure at CERN? Like, for example, as a condensed matter physicist, what I do, let's for example in microscopy, I'm seeing the scattering of electrons to know more about the crystallographic structure. I am seeing the tunneling of electrons through my substance to have a better resolution at atomic scale, something like that. So I am using electric field, electrons and photons to to explore the physics. What exactly do you measure at CERN?
In very simple terms, we are measuring only the energy and momentum of particles. This is the very simple answer. What happens is you collide two protons, and then because protons are not fundamental, as I mentioned, there are quarks inside them. These quarks are also what we call gluons. I don't want to get into too much detail. I know it's very expensive.
Okay. For now, it's what we can say, at least specifically for this podcast, is that there are particles which exist beyond photons, and the physics behind them is very rich. So for now, we just want to confine ourselves to the point that there exist particles beyond photons. But for now, we are using photons as a topic of discussion.
So from protons, the particles collide, and then from the collision, there are new particles coming because you have so much energy. So because Einstein said energy is equivalent to mass, you can create heavier particles with this energy, and those particles, because they're heavy and unstable, they will decay. And the decay products will basically fly through our detectors. And when they fly through our detectors, we measure what points they are flying through. So we have a tracking detector, for example, and these tracking detectors also measure their momentum of so basically the speed at which they were
speed at which they're moving. Okay,
exactly. And then after the tracking detector, behind it we have a huge calorimeter which measures the energy of these particles that come out. And then we have another tracking detector for particles that we missed or that haven't been stopped in the calorimeter to measure their momentum again. And after we have done all of this, then there is a complex algorithm in the software that basically reconstructs the entire process to see which particles flew out, what vortex they were coming from. So there's a lot of vortex matching, and then they reconstruct the entire process of two protons going through this heavy particle into these decay products. And then you have the full event of a.
So basically, what we have is a series of multiple detectors for different type of particles. Like for example, in a very crude way, it would not be wrong to say that we have neutral particles, negatively charged particles, positively charged particles, and particles with specific properties. So we have detectors for every single type of particles. We collide the electrons together. Then we have multiple detectors spread all around the CERN, which detect different type of particles, and the information about their momentum, their position, and their energy. If I get it correctly.
So just one thing, that it's not spread all around CERN. So CERN is the lab, the full area. Then you have Large Hadron Collider, which is the collider ring, and then on the ring there are 4 points where these protons collide, and at these 4 points you have 4 detectors, 4 different detectors.
See.
So these are 4 independent experiments.
These are 4 independent experiments.
Exactly.
Okay. So what is the most interesting thing that in your PhD that excited you, during this CERN experiment?
During my PhD?
Yes.
I am not prepared for this question. No,
trust me, nobody. As a PhD, nobody is.
To be honest, because the thing that actually excites me the most is not. Of course, the physics behind it is very interesting, but the physics is something that is going on in the background all the time. So you know that you will be doing physics. So it's that excitement is there as a baseline. But on top of it, what interests me most is the methods that you use to actually achieve those physical results.
You mean the concept of the algorithms and the creation of algorithms,
the softwares that you prepare, the algorithms you write, and the methods you use. How creative you can be to actually get more precision in your measurements.
I see.
That's what really interests me most in this process. The physics motivation, of course, if that wasn't there, I wouldn't be doing a PhD. So that's the baseline that has to be there all the time.
You have to be excited to explore the possibilities with the help of physics.
Exactly. Yes.
Yeah, that's definite. I think that's one of the the building pillars.
Yes, exactly.
To start to do your PhD.
Yes.
Yeah, that is so true. Okay, so I have one more personal question actually. It's related to Atlas.
Okay.
So for our audience, let me tell you, Atlas is one of the biggest sections of CERN, and
It's one of these 4 experiments that I
it's one
mentioned.
of the yes 4 experiments. Because the reason why I'm interested in knowing more about Atlas is because it's more of like a the face for for publicizing the CERN experiments, because every time in no matter in what magazine you're talking about, you always see the picture of Atlas. So I want to know, what is Atlas?
Okay. So the reason, first of all, is just saying the reason why Atlas is the face in this sense is because Atlas is closest to the CERN area, the lab itself. So there is another experiment which is, I personally would say, is doing really a similar research project, but it's important to have a competition and also cross checks. So it's on the other side of the ring, so it's so far that people can't get there. That's why it has less publicity. But yeah, Atlas is one experiment that is general purpose. So it tries to look for pretty much everything that you can see from the standard model, and that's why it has so much publicity. It's the biggest experiment in size, and also I think also money in the costs the most. But it's still, fun fact, it's huge, but it will still float if you put it in water.
That's interesting.
Yeah, it has a very low density, the entire experiment itself. But it is what I was describing with this experiment, that you have a tracker, the calorimeter, and then this other tracker. That's basically the structure of Atlas as well, because I work with Atlas. So, so that's why.
So you extract data from Atlas and then you
exactly analyze it.
Yes. Okay. Interesting.
Yes.
Okay. So my next question is, how a non-scientific person can associate himself with the research that is going on in particle physics? You know, for a lot of people, you know, some example which
the simplest association, at least for people in Europe, is that it's their money. It's the taxpayers' money that is funding all of this. But coming from the physics point of view, I mean, so the thing is, because the research that we do needs so much of technological, has such huge technological requirements, there are a lot of spill-off effects from this research. For example, the detectors that we build for these tracking on and reconstruction of particles, it's now being used for security systems where basically if a truck is passing through, they can do the entire X-ray scan at once. It wasn't possible to do it at once before because they needed very fast tracking reconstruction. And we built it for our detectors, and that's why it's possible.
That's why it's like a spin-off research that helped.
Exactly.
Yes, okay.
Exactly. So
that's interesting.
Then,
I see.
Then the biggest example is, for example, the World Wide Web, which was developed in CERN for easier communication of data and data transfer within the campus. And then because it was so successful, they released it publicly, and now everything happens on World Wide Web on the internet.
That is so interesting. I mean, it is really, really interesting that World Wide Web, not everybody knows that it originated in CERN.
Yes.
Okay, this is cool.
So there are a lot of spill-off effects from the research going on at CERN.
There is also one, sorry to interrupt, but we actually use it sometimes, occasionally, the neutron scattering experiments. They also happen at CERN, and neutron scattering experiments have extensively helped condensed matter physicists to explore more about the surface phenomena that are happening, like the crystallography and all these things.
Sure.
So
I mean, there are, so CERN, for example, is LHC is one project, but then there are a lot of other experiments which neutron scattering, also neutrino experiments, some electron beams, a lot of stuff. So there is a lot going on, and there are a lot of industrial application for the technologies that we build. So in current times, this is the direct connections that a person from non-scientific background can associate to.
I see. So it's not the waste of taxpayers' money, first of all. I mean, not fully, I would say.
Yeah, I mean, it's a matter of how much we make out of it in the future, of course. But at the moment, there's a lot of industrial applications. Then another thing is that because there are so many people working at CERN, data analysis, hardware, whatever they're doing, and in such extensive environments, they have an amazing training to get into industry after that, for data analysis or for building hardware in industry. So it's basically also creating a workforce for industry.
For industry. So that's where actually we are heading towards that. What are the possibilities of after doing a PhD or after doing a master's in particle physics? What are the possibilities of going or entering into the area of industry? And what are the industries that are there who use such type of skills?
Yes. So somewhat depends on what you did in your thesis, because where your specialization is. So if you do something like hardware, when you're building
detectors and sensors, yes,
exactly, then you get into an industry that also works on optics or electronics, scintillators, sensors, all sorts of these.
Yeah, I mean, nowadays the industry of sensors is booming extensively.
Exactly.
Yeah.
If you do data analysis, what I'm doing, then data analysis is everywhere.
Yeah, data science, data science, AI, machine learning is everywhere.
You can do anything in those fields, because
Yes.
the amount of data that we have is basically, you won't find it anywhere in industry that this large. Even Google has less data than what we have.
Then CERN. So,
okay.
now my question is, when you say data,
Yes.
what do you mean by that? Like, for example, in a very layman language, a data is a set of lists.
Yes.
You know,
Exactly.
That's what a data is. What type of data that you collect from CERN?
It's just these momentum and energy measurements for different particles, in principle, in very like nominal way, or very simple words.
So one is X, Y, Z, P, Px, Py, Pz,
Yes, exactly.
and their errors, delta P, delta P.
Exactly.
Yes,
in
exactly.
principle, just that, and then you have this is the raw form of data that comes out, and then there's a complex algorithm that converts these into events. So it does the entire reconstruction and vertexing and everything, and that's what we get in the end. So we can basically identify as a particle as saying that I can say that this is an electron with certain probability.
I see.
So this is what we get in principle, and that's what we work with. But already, for example, the fits that we do, the statistical fits have 250 parameters, for example.
250 parameters.
And with error handling, right? So this is nowhere in industry you will find this. It's already a very complex analysis that's going on.
I see. Yes, indeed. And how exactly the involvement of AI and machine learning has changed or has advanced the particle physics in this upcoming time?
So I would start with saying that at least neural networks and machine learning is nothing new to particle physics. Also, if you see analysis that were going on at CERN in 80s, they were still doing machine learning with boosted
in 80s
with boosted decision trees and everything. That was still going on back
then.
then.
So the concept of neural networking and machine learning was already introduced in the 80s.
And in a lot of sense, the boom in machine learning and neural network was really created by a lot of fundamental research. Because we had so much data, we needed something to actually analyze it. So we started working on machine learning. Neural networks, of course, came a bit later, but the initial machine learning algorithms were already there. But now with artificial intelligence, of course, this makes things, I would say, easier for us, because now, let's say, debugging our code or writing code becomes so much easier.
Exactly.
Yes. So let's say the generative AI, the artificial intelligence now is helping us a lot with newer, or with writing our code, with making our everyday activities easier. But just this use of neural networks, it was going on since a long time. We've been doing it from almost the beginning.
It is really surprising to me that so many things have originated from CERN.
Yes.
This is cool. It's very eye-opening for me.
I mean, it's a huge community. They're doing a lot of things. So
yes, indeed,
it's a matter of fact that something comes out of it.
Yes. Okay, now the next question that I would like to ask is CERN the only experiment that the particle colliding experiment that is happening inside in the world, or there are other particle accelerators? For example, in India, we also have one particle accelerator that started, I think, in the early 1960s, if I remember it correctly. This is one question, that are there any other particle accelerators? And the second question is, what are they detecting?
Okay.
Yeah.
So there are a lot of particle accelerators, as you mentioned. There's been one in India, maybe even more. It's a matter of the energy scales, for example, what energies do they explore. It's a matter of also intensity, how intense and strong the beams are, but then also what they are accelerating. So at LHC accelerates protons. Right?
Protons, yes.
There are, for example, in Japan, there is another accelerator called Super Keck, which accelerates electrons and anti-electrons.
Anti-electrons, the particle and antiparticle.
Exactly. So they have an electron-anti-electron accelerator, what we call anti-electron is called positron, just for the term. And then they detect processes that come out of that. So they have the difference in that is the proton, as I mentioned, is not fundamental itself. It's made of quarks. Yeah. Electron is fundamental. So now you're colliding fundamental particles, and it makes the environment of research much more cleaner.
So
you have less of these all the background that is going on in behind your signal process. So you have to do less searching, but they have their own restrictions, which protons are easier with. So so you do all sides.
Basically, the energy is one of the fundamental
exactly.
things,
So
right?
you can't push electrons to a very high energy, because then the accelerator becomes huge. You really need a much bigger ring for it.
Okay.
Then there are accelerators in the US. For example, there was a small overlap of timing as well with the Large Hadron Collider. They had this accelerator called Tevatron, which was running, which used to accelerate protons with antiprotons and collide those. So that's also a different environment. It's still protons, but it's colliding with matter instead of matter.
But if I understood, as far as I know, when there is a collision between matter and antimatter, there is an origination of pure energy.
Yes.
Right.
Yes.
And energy. This is what I understand. But then, what exactly are we exploring? We already know that matter and antimatter, if they collide, then it's gonna create energy.
Yes.
What
so in
exactly
most cases,
are we looking for?
In most cases, for example, if you collide an electron and this antimatter positron, you will get a photon. It will generate a photon.
Yeah.
But that photon has so much energy that it's also not stable, so it will decay in different ways.
And then
you can measure it. But if you go high enough, which is mostly the case now, you can create other bosons or other interaction particles for other forces. For example, the weak force. There is this boson called the Z boson.
Z boson, yes.
So you can start creating that, and of course that the Z boson itself is massive and it has different ways of decaying than a photon. So then you can study those processes as well.
Okay. So basically, these different type of other than CERN, these different type of accelerators are exploring different possibilities of different mechanisms of decaying of different particles.
Exactly. They have different sensitivities to different processes.
Processes.
Then and I would say not even just colliders. Actually, one of the most interesting things that are happening right now are neutrino experiments.
I see the ice cube experiment.
Exactly.
Yes,
and
I was about to come to that. That's good that you have already started talking about it. Yeah.
So these are a different kind of experiments that sometimes need an accelerator, but mostly don't. So, for example, the ice cube experiment that you just mentioned, it's a huge experiment at the South Pole, which basically puts like detectors in the ice. The reason they have it in the ice is because you need huge volumes for neutrinos to actually interact.
Yeah.
And then if it interacts and creates a particle, these detectors will detect it. And for this, you don't need a beam, because in the cosmic environment, in the background, in the universe, there are so many neutrinos flying around. I think for comparison, they say that there is about 1 billion of neutrinos passing through your thumbnail every second.
Yeah.
So you don't feel it because they interact very, very weakly. But yes, there is a huge amount of neutrinos flowing everywhere, so you don't really need a beam. But if you want, so there are some experiments where, for example, if from CERN, the beam that you get, you can after you dump the beam, you can create some magnets and remove all the charged particles. So then you get only neutrinos flowing through. And then these neutrinos, if you point it well, this is actually done. You point it towards some experiments in Italy, in Gran Sasso. So from Geneva all the way to Italy, these neutrino beams travel, and then on those experiments you detect these neutrino beams.
Interesting.
The reason for doing this is this phenomena called neutrino oscillation. So
they change colors.
Yes.
That's a very interesting concept that I studied in my masters.
Yes.
I was very fascinated. I was like, okay, this is nice.
I love neutrinos actually.
Yes. So for our audience, what are neutrinos? Neutrinos are again one of the fundamental particles, I would say. The interesting fact about them is that they are negligibly interacting, which makes them very interesting. This is one of the reasons why neutrinos got a lot of attention in the area of astrophysics, because the neutrinos which are created during the starting of the universe, they are still there. They are still here. So that's what make the study of neutrinos very fascinating.
Another reason why it's so interesting to astrology is
astrology.
A
typical Indian.
Astrophysics. Yes. Okay, my brain is fried already from the last week. To astrophysics is because they are looking for something like dark matter.
Yes.
And dark matter is very close in some sense to neutrinos, because it also very weakly interacts. The only thing is that neutrinos have such low masses that they travel almost at the speed of light, and that's where dark matter differs. So dark matter is supposed to be heavy so that it can have gravitational fields around it, and that which makes it slower than speed of light.
Okay,
Yeah.
you have already initiated one of my,
This will keep happening, I think.
Yes. I mean, I'm really happy to, you're already, without me even asking you about all these things, you are already...
Everything is so
Yes.
linked to the speed.
Exactly.
Can't help it.
So, the concept of dark matter,
Yeah.
it has attained a lot of publicity
Yes.
in the recent time. So, the concept of dark matter, as a person who is not really into the subject, what I understand is that only a few percentage in the universe is containing of matter.
Yes.
But the remaining part is occupied by dark matter. This is what I have read in the science fiction and all these things. But now the thing is, dark matter is something that you can't detect, at least till the moment. But then how do you know that it really exists? Is it really the hypothetical concept, or is it really something that is created from the theory and now you're trying to prove it in the real life?
No, neither of them actually. It's there. We have seen evidence for. So let's say there are evidence of seeing things that do not behave as we expect them with the normal amount of matter that we see. So there has to be. So we expect. Again, it's a theory because we haven't seen it, right? So we expect there to be more matter, more mass around, which will then be explained by, for example, dark matter, because it doesn't interact in the normal way. That's what dark matter is hypothesized as.
Okay.
The reason that, or the fact that we haven't seen it yet, allows for actually a lot of models for dark matter. There are actually a lot of them going around, and even the mass of dark matter has a huge range. It goes from, I don't know, 10 to the power -3 to 10 to the power 10 to the power 7 electron volts or something like this. So maybe even more, 10 to 11 electron volts actually. So it's a huge range of mass, and then there are models for each mass saying, or each range of mass saying that this can still explain dark matter with different properties. Okay. So there is a lot of possibility for dark matter. We haven't seen it yet, but there is very strong evidence that it should exist.
So okay, correct me if I'm wrong. I have read it somewhere that how the Higgs boson was detected, and the theory of the concept of dark matter, people are trying to explore it by colliding particles and then analyzing the decay of those particles with the help of different detectors. They collect all the data, combine it with the equation of E is equals to mc square, and then if there is some extra amount of energy which is coming, they can associate it with the origination of different particle, like in the case of Higgs boson, or it is the reason why we need the concept of dark matter. Is this correct? This is the way we explore.
Partially correct. So, for example, the idea is that we know energy should be conserved. So you know what the initial energy is because you're giving the energy to protons, and then in the end you reconstruct the entire event with this reconstruction and vertexing, and then you can build the total energy that came out of that event. Now, if there is an imbalance of energy, you can say that there was something that we did not manage to detect.
I see.
The problem we have is our detectors cannot see, or the detector at Large Hadron Collider cannot see neutrinos, because again they are very weakly interacting.
Yes.
So most of the time we associate this energy that is missing as energy coming from neutrinos, because that flew off in the event, right? But of course this can also come from other particles that we cannot see, for example dark matter. So this is, in most cases, searches for dark matter, at least at the LHC, will associate them as additional missing energy than what you even expect for neutrinos.
So there is still a missing piece which still exists, which we are not able to. We are naming it as dark matter.
Yes,
in simple words.
Exactly.
Okay, I see. Now I will
dark only because
we don't know about it. We cannot,
dark because it doesn't interact with light.
Okay.
Because it doesn't have an electromagnetic interaction, so there's no light coming out, and that's why it's dark to us.
But then my second question is, if it does not have an electromagnetic interaction, then what type of interaction does it have?
It can have weak interaction, which is again very weak, or it can have gravitational interaction.
Again, the origin of graviton.
Yeah.
I love it.
Exactly.